Yeah.
Okay, perfect. So welcome everyone to this special edition of the Isogeny Club, or the Lattès Club today, where we are lucky enough to have Dr. Marzio Mula giving a talk. He is a postdoc at the Universität München, and yeah, he will be talking about the Hessian as a Lattès map. So please, Marzio, take it away.
Thank you, Jonathan, and thank you both Jonathan and Maria for inviting me here for this very nice cycle of talks. So yes, as the modified logo suggests, today I will not really talk about isogeny graphs, but I will still talk about graphs made of j-invariants, so something that we all might enjoy anyways. And this is a joint work with Federico Pintore and Daniele Taufer. We have a preprint already online that I will link later. And there is an upcoming new version with some more details in it. So yeah, I will start my talk by just recalling the definitions of what is the Hessian map. So we will start with the Hessian of a cubic because it's a construction that works over geometric objects. And then we will try to view the Hessian also as a map over the modular cube of level 3. So something operating on isomorphism classes together with three torsion bases. And only then we will view it also as a map on j-invariants, which will be actually the main thing we will consider later on in the talk. And in particular, we will try to see what happens if you keep iterating the Hessian operation over the j-invariants. And what we found out, or actually rediscovered, as I will later explain, is that this map is a so-called Lattès map. So it falls under a family of maps that are quite well understood. And this will allow us to understand how to draw these graphs more precisely, which will constitute the last part of the talk. So again, I repeat the disclaimer that these are not isogeny graphs. We are still trying to understand if there is any relation between Hessian graphs and isogeny graphs, but this is still probably part of the open problems that we are looking at. Okay, so let's start with the definition of the Hessian of a cubic curve. So differently as I did in a previous talk I gave at the Isogeny Days more than 1 year ago, I will work today on a generic field, so we don't need to restrict immediately to the finite field case, which will be only the last part of this talk. And well, the Hessian of an algebraic variety is something that can be defined much more generally than I will do now. But what is special about the Hessian of a cubic is that it still gives birth to another cubic. So it preserves the type of geometrical object you started from. So what you do to construct the Hessian, you start from a cubic with some equation given by a polynomial. You just write down the so-called Hessian matrix, so the matrix of the second degree derivatives, and you take the determinant of this matrix. And the determinant is what we will call the Hessian of E. So it defines itself a new polynomial, which defines another cubic. Okay, so we have a map going from cubics to cubics. What is the relation between an elliptic curve and, or more generally, a cubic and its Hessian? Well, the intersection is actually a set of inflection points of the object you started from, of the cubic you started from. And in the elliptic curve case, this will be exactly the three torsion of both objects when they are both elliptic curves, of course. We will soon see that it's often the case that if you start from an elliptic curve, you obtain another elliptic curve when computing the Hessian. Just to give you the picture of this, well, it's hard to give you a picture that shows all the 9 inflection points at the same time. I guess it's actually impossible. Yeah, notably, I chose a special shape for the starting curve and the Hessian, so that it's kind of the same shape. We will soon see how to do that. And yeah, you can see that the inflection points are those where the curvature changes, and this is visible in the picture. Of course, you don't see, as I said, all 9 of them, but you can still ask Sage to compute them. And these are the 9 inflection points that are the 3 torsion points on the 2 curves. Okay, so this suggests that if you want to pick a good form for the elliptic curves, so that when you compute the Hessian, you have still an elliptic curve in the same form, we need to force the elliptic curves to pass through these 9 points, right? Because in this way, also the Hessian will still pass through these 9 points. And this is actually the idea behind the definition of what is not by chance called the Hesse pencil. So the general way to construct the Hesse pencil is that you pick 9 points. You have to be a little careful on how you choose the points. But yeah, the usual choice is just to pick the inflection points of a starting elliptic curve. And then you parameterize all the cubics that pass through these 9 points. So what is usually done, you pick this cubic, which is usually called the Fermat cubic. Maybe there is a different sign for the last entry, but I would call this the Fermat cubic. And in order to parameterize all the elliptic curves going through the inflection points of this curve, you pick the curve itself and the equation of its Hessian, which is x, y, z. And you pick all the linear combinations of these 2 equations. And this is indeed the Hessian form of elliptic curves for fixed values of lambda and mu. And the whole set of these curves is called the Hesse pencil. Of course, one might ask, okay, when does this represent a smooth object or not? Yeah, this corresponds, of course, to specific values of mu and lambda. Okay, some fun facts that I only recently learned and which are hopefully true. Well, the Hesse pencil is a model for the modular curve of level 3. So these values of lambda and mu actually encode pairs of isomorphism classes of elliptic curves together with torsion bases. And even better, if you take the cubes of them, they still encode something meaningful. So isomorphism classes of elliptic curves together with cyclic groups of order 3. So it's kind of nice model if you want to consider 3 isogenies. Okay, but why am I introducing this? Okay, as we said, the Hessian of an elliptic curve shares the 3 torsion points with the elliptic curve. And this seems to be the right model to look at the Hessian. In fact, if you start from a bias transform, this is from maybe one of the forms we are more used to, and you take the Hessian, you end up in something that doesn't look super nice in general. So it's not in the same form. While if you start for something in the Hessian form and you take the Hessian of this curve, you obtain something that is again in Hessian form. So this shows you that you can express the Hessian as a map over the modular curve of level 3. So you can just look at how the Hessian behaves on the coefficients of the corresponding curves. And the map is the one I've written below. So it's a map of degree 3. Okay, so this gives you the picture of what the Hessian does on x3 as promised. But what does it do on x1? So if we look at the level of j-invariants, well, the good news is that the Hessian does not depend on the representative of the isomorphism class you pick. And therefore, the j-invariant of the Hessian of a cubic, of an elliptic curve, depends only on the j-invariant of the starting cubic elliptic curve. And this is exactly the formula that I wrote here. There is only one special case in which the Hessian of an elliptic curve is not an elliptic curve anymore, and this is the case of j-invariant 0, in which case one can directly check that the Hessian is the union of 3 lines, so it's highly degenerate. And this union of 3 lines will be what we will call the point at infinity in the remainder of this talk. And what happens to the point of infinity? Well, if you start from the union of 3 lines and you compute its Hessian, then you get again the union of 3 lines. So the point at infinity is just mapped to itself by the Hessian. Okay, so the bottom line here is that the Hessian also acts as a map on P1, seen as the set of j-invariants together with the point at infinity that represents the generate case. Good. So yes, finally we get the first teaser picture for the remainder of the talk. So what we will try to do is to iterate the Hessian over, especially over the j-invariants, but we will also keep an eye on the Hesse pencil, at least for a while, and see what picture we get. And what motivated us to investigate this was that when we tried to draw the graphs over finite fields, we noticed that these graphs were extremely regular. So they had lots of internal symmetries. Okay, so let's start from a more general introduction to functional graphs. Because at least for us, it was really unclear when we first saw these pictures, if this was just something that always happens when you look at any rational map or a finite field, or if there was anything special about it. So we were quite far in from understanding functional graphs in general. So let's introduce functional graphs over fields. So we pick any fields except from characteristic 2 and 3 that I barely know. And we pick a rational function over this field, which we call phi. Generally, the functional graph of phi is just a graph where you put all the elements of the field and you connect 2 elements by an arrow if and only if this element is mapped to the other by the function phi you chose in the first place. You have to be a little bit careful. You might want to draw like multiple arrows to count some sort of notion of multiplicity. I will introduce it a bit later because it's useful for the remainder of the talk, but it's not very significant for now. So let's take a look at the functional graph of x squared, for example, over f7. And this is another example of graph that is quite nice and regular, as you can see. However, this is, luckily for us also, this is not always the case, as we will soon see. Yes, okay, you have also to deal with the denominators, which that do not appear in the example I've just shown, but so that's why you need to introduce this point at infinity. And yeah, the point at infinity can be a little more tricky. Maybe you need to move to the projective version of the map, or you might even want to move around, to change the variables on the projective plane to see the multiplicity more easily. Okay, so this is an example of graph that is not nice because you can see that it's much less symmetric. But there are properties, of course, that are always true for functional graphs. So, for example, you cannot have more than one cycle. And, well, for functional graphs over finite fields, you are doomed to have cycles on every connected component because you cannot go on forever on a finite field. We can also tell something about the in degree, which we expect for every vertex, because of course it is dictated by the degrees of the polynomials appearing in the rational function. And well, the out degree, yeah, it's usually 1. When it's not 1, it's just because of multiplicity issues. So in the pictures we will see later, I will not draw the multiple arrows. But as I said, they will turn to be useful for a special criterion we will soon see. Okay, so as also this picture suggests, in general, we do know very little about a functional graph. However, there are situations in which we, on the other hand, know a lot. We can deduce a lot more about the functional graph of a given function. And the situation in which this happens is when you have some more regular object above your rational function. So whenever you have an algebraic group on top, and the rational function is a sort of projection of a group endomorphism on the top, then you can easily, you can understand more easily the structure of this rational function. And this is the case for the so-called lattice maps. In this case, the group above is an elliptic curve. And note that I will introduce lattice maps using the algebraic closure of the field, while later on we will need finer results in order to understand what happens over finite fields. And other than the elliptic curves, as I said, you also need a group homomorphism. So you need a morphism of the curve, which is the composition of an endomorphism and a translation. And finally, you want to have a projection that maps everything down to the level of the field where the rational function is defined. So, okay, a map phi that satisfies this commutative diagram is called a Lattès map. Okay, so even though the definition might seem quite far from the intuition, so how can you find this elliptic curve? Given if I give you phi, how can you find the elliptic curve, the morphism, the projection? It's quite hard, and actually we had to spend quite a lot of time to brute force it. But actually, if we had been experts in dynamical systems, we would have known that there is an easy criterion, at least over C, to tell if a rational map is a Lattès map or not, which actually requires you to look just at a bunch of points of the rational map. So some points are the exceptional points. So the exceptional points, are usually not so many as the name suggests. I think they can be at most 2. And the set of exceptional points, and they are the elements of the largest finite set that is kind of mapped to itself by the function and does not have any predecessor outside from the set. But the most tricky part is if you want to have a lattice map, you need to be able to construct this so-called ramification function that needs to take into account the ramification at points. So you want that this function is almost everywhere 1, but as soon as you encounter a point with the multiplicity larger than 1, you need that this function reflects this on the next point. We will see this in an example, which will make everything more clear. But yes, so you only need to consider the points that come after a point where the derivative of the rational function was 0, essentially. And these points are called the post-critical points, exactly because the points where the derivative annihilates are, where the derivative vanishes, are called critical. And therefore, you only need to inspect a finite amount of points in order to tell if a rational map over C is a Lattès map or not. Okay, so let's use this over the Hessian function and see if it is a Lattès map, at least over the complex numbers. Okay, after some computations, one can check that the post-critical portrait of the Hessian map over the j-invariants, which is the last one I defined in the previous part of the talk, is exactly the picture I'm showing here. So yeah, notably the weird numbers are multiples of 1728. So yeah, these multiple arrows that are capturing the multiplicity. I will not draw them in later pictures. But what we want to do, okay, to use our criterion, we want to define this ramification function. As I said, you can just not care about the value of the ramification function outside of these points because it will be always 1. But when you encounter a critical point, you want that the ramification follows the number of arrows starting from it. So here we have 3, so we have to set the ramification function to 3 here. Here we have 2 arrows, so we need to multiply it by 2. And here there is only 1 arrow, so it's consistent, and the 6 stays where it is because it's multiplied by 1. And the same here, more simply, you just have 2 arrows, so you need to multiply by 2, and then you stay there because there is only 1 loop arrow going there. Okay, so since you can also check that there are no exceptional points, then you use the previous criterion to conclude that the Hessian map over the j-invariants is a Lattès map. Okay, but this is kind of not fully satisfactory because we still don't have an explicit elliptic curve, an explicit morphism of that curve that projects onto the Hessian map. So since we need final results, it is actually useful to try to be more explicit here. And this is what we did. So we tried to be more explicit in order to achieve more general proof of the Hessian map being a Lattès map that works in any characteristic. I'm actually quite sure that the criterion I presented over C also works on other characteristics, but since we are not super familiar with it, I will still claim that our proof is slightly more general. But for sure, what you gain if you use a finer diagram rather than just the Lattès diagram over the algebraic closure is that you can understand more precisely what is going on fields that are not algebraically closed. So finite fields, but also number fields, you get some information. And in the case of finite fields, well, it's you get some information on how easy it is to compute iterated Hessian. Because if you can show that it descends from an operation on an elliptic curve, and as we will see, this operation is kind of the square root of -3, then it's quite easy to compute iterated Hessian. And in some cases, it might be even easy to tell whether two j-invariants, for very large primes, whether two j-invariants lie in the same connected component. The next question will be, is this of any use? We still don't know, but at least it's interesting to check that the Hessian and iterated Hessian is a simple operation, even for large primes. And yeah, okay, in the last part of the talk, I will also share some fantasies on supersingular elliptic curves. So we try to see in which parts of the Hessian graph the supersingular j-invariants fall. And interestingly, there is something you can say which is derived from our results. But yeah, so far the feeling is that it's still not enough to do anything. So in particular, it's not enough probably to either find the supersingular j-invariants out of the blue or to even compress them in some way. But we could also discuss that after the talk if someone is interested. Okay, so as I said, we try to be more explicit in our proof that the Hessian is a Lattès map. I will introduce now a parameter k, which is just to deal simultaneously with the Hessian of j-invariants and the Hessian of the Hesse pencil, because the models are kind of the same, but they change up to a parameter, as we will see. Okay, so the ingredients we need for a Lattès map are, first of all, an elliptic curve. And in this case, the elliptic curve is the one with equation y² equals x³ plus k over 4. And we also need a morphism on the curve, which in this case will be an isogeny, so an endomorphism in the sense we all usually use. Whose kernel is, again, explicit, so it's just points with the first entry equal to 0. And the last ingredient we need is a projection. Of course, you can do that arbitrarily, but what is interesting is that for specific choices of k and of projections, we exactly get the Hesse pencil, the Hessian map over the Hesse pencil, and the Hessian map over the j-invariants. So, okay, this is the explicit picture of the Lattès diagram in the case of the Hessian transformation. Two further remarks. Okay, the first is that the j-invariance of the model curve is always 0, independently of k. And this will help us to do computations, because at least when this j-invariant is supersingular, which is quite a lot of situations, you can even deduce more about the structure of the Hessian graph. And unsurprisingly, we will see that actually over finite fields, the Hessian graph looks more regular when when 0 is a supersingular j-invariant. And the second thing I already mentioned, that I will stress it again, is that this endomorphism is exactly the square root of -3. So it's particularly nice. Okay, speaking of nice, let's now start our path towards drawing the Hessian graphs. So, okay, we built our nice commutative diagram. But now what can we actually say about the group endomorphism on top? Because yeah, we claim that understanding the dynamics of group endomorphisms is easy, but yeah, let's see how easy it is. In order to describe what's going on the elliptic curve on top with the action of these endomorphisms, we will need these built-in blocks that are called big T. I will also call them big tree because they do look like big trees. They're actually complete trees, except probably from the first branch. So you have something of finite depth or infinite depth, but then you have no leaves at all. I'm sorry, yeah. And yes, as I said, it's almost complete in the sense that you have only one branch less for the first root, and then you always have these three things. Okay, yeah, the definition is given more generally for arbitrary L, but of course we are in the case of, in our situation, we will need L equals 3. Okay, so let's take this as a more general exercise. So we have a group. It doesn't matter if the group is finite or not. And we have an endomorphism over this group whose kernel is prime. So again, L is 3 in our case. Okay, we define this tau p, and in particular, we define tau 0. Tau 0 is the set of points which are eventually mapped to 0 if you iterate the endomorphism. And tau 0 is kind of the main block you have in the structure of the dynamical system corresponding to psi. So specifically, tau 0 will be a big tree with some depth. The depth might also be infinity. And all the rest is kind of dictated by tau 0. So there are 3 possible connected components. One is just a cycle, and every element in the cycle is the root of a copy of tau 0. This is the first situation you can have. Another situation you might have for the connected components is that you have an infinite line, so it's infinite in both directions, and every point on the line is root of a copy of tau 0. This is the second situation you can have. The last situation is that you fail to have a complete line, but you still have a semi-line starting from some point and going on. And as you can see from the picture, the first point has nothing, the second has a smaller tree, the third is a bigger tree, and they grow until they reach the depth of tau 0. So this is probably the less intuitive situation you can have. And this is the complete picture of what can happen. We actually didn't manage to find an example in which the Hessian graph reflects all of these possible scenarios. This will require to work over fields of characteristics 0, because yeah, of course, on the finite fields, you are forced to have only cycles. But we found examples of group endomorphisms more generally that reflect all these possible situations. So yeah, the description should match all the possible cases that occur. Okay, so all of this chaos was to just understand what's going on top of the Lattès diagram. So this means that as soon as we deal with subgroups of the model curve we are using, then we know pretty well how the endomorphism behaves. So we know that, for example, when we have loops, we will have only big trees of fixed length attached to these loops. The issue here is that we want to look at the rational function over non-algebraically closed fields. So the question is, when we move from the Lattès diagram, which was over an algebraically closed field, to its non-algebraically closed field version, what is happening? We need to understand how the pre-image of the projection looks like. Because if it is a group, then everything follows easily from what we found about CK. But if it's not, you need to be more careful and consider the subgroups that form this pre-image. Okay, so we actually had 2 projections to deal with because there was the projection for the, let's go back to that because I forgot to stress it. Yes. yes, we had two projections to deal with. So the projection for the Hessian pencil was quite easy. So you pick a point on the elliptic curve and you just take its first coordinate. And it's slightly more tricky in the case of j-invariant because you not only forget the second entry of the point, but you also cube the first entry of the point. So this cubing operation adds a layer of difficulty to understanding the Hessian map. Okay. So this motivates to define these sets, which are unsurprisingly candidate to be the pre-image of P in both cases. So the first one is the set of points on the elliptic curves whose first entry belongs to the field you want to consider. And the second SK is just the elements of the elliptic curve whose cube of the first entry belongs to the field we want to study. Okay. So this that I'm now showing is the actual version of our Lattès proof about the Hessian map. So we proved that this diagram is commutative. So we got rid of the algebraic closure, and we are instead considering this pre-image that we built in order to have the commutative diagram. And again, if you plug in the values that I gave you also before, you get in one case the Hessian pencil. And if you move to the other settings, so you take the other pre-image and the other projection, and you plug in the value corresponding to the case of j-invariants, you again obtain a commutative diagram. So this is just a refinement of the statement on the Hessian being a Lattès map. But the advantage is that it is taking into account the specific field we want to work over. Okay, so as I said, we understand now how pk works over the elliptic curve, as long as we consider subgroups of the elliptic curve. So are these two these two big S, so these these pre-images of pk actually subgroups of the elliptic curve? The answer in general is no, but we will now see how they are made of subgroups. To do that, we need to consider the twists of the elliptic curve. So we pick the classic twisting parameters and we map the curve to some twist. And let's see how S is made. So if you look at the pre-image of the projection involved for the Hessian pencil, then S is just made from the pre-images of the quadratic twists. In particular, you have to take the k-rational points on the quadratic twists and bring them back to the starting curve. And this is S. And the other S is completely similar. So it's just made of the pre-images of the sextic twists. Okay, this is probably all we can say in the case of, in the general case. And now we can finally see what happens in the finite field case. So how all this machinery can be used to understand the structure of the Hessian graph over FQ. Okay. Furthermore, so far I tried to consider both the Hessian pencil and the j-invariants. Now we will only focus on the j-invariants, which are actually harder because you are taking this cubing operation before. So the situation might be slightly more complicated than in the Hessian pencil case. So for the values I showed you before, if you plug them into the general formula I gave you, the model curve is this one. So y squared equals x cubed minus 1728. So very nice because b equals minus 1728, but the j-invariant is again 0. And yeah, I will simply denote by S the weird set S that I introduced before. So the pre-image of the points of the j-invariants through the projection that makes the Lattès diagram commute. And what are the benefits of looking at Hessian graphs over finite fields? Well, first of all, they are super nice. They're super regular. And with the machinery we introduced, now we can kind of color the graphs according to which twist gives rise to the points in the graph. So in this example, we have 6 colors. The white points are those coming from the key rational points of E, and the other colors come from the key rational points of the twists of E. And we will differentiate cases depending on how many twists are involved. This depends on the field. And yeah, the other advantage of working with finite fields is that even without computing explicitly the Hessian graph, we will be able to deduce their structure just from the theorems I will shortly introduce. And just by computing the points on En over its twists. And finally, as I anticipated, there is the special case when E is supersingular, so when P is 2 mod 3, in which you even get more information. Okay, a first property that I want to recall, because we already knew that before understanding all this Lattès map thing, is related to the traces of the elliptic curve in the Hessian graph. So just forget for a moment about the Lattès map machinery. If you just look at the traces of the elliptic curve in the Hessian graph and you take their absolute value, because yeah, you're kind of blind to the twists, at least in this representation of the graph, you notice that you have odd traces on the leaves. So the second entry in this picture is the trace, the absolute value of the trace. You see that there are only odd traces for the leaves and only even traces outside of them. And this is actually something that one can prove just by looking at the equation of the elliptic curve and its Hessian. So I think that it's because the Hessian kind of produces some subtorsion point over K. It might be something like this. Okay, but let's go back to the Lattès map thing. So how can we use all the machinery we built to understand the structure of Hessian graphs over finite fields? Well, we have 2 cases. Let's start from the nicest one, which is Q equals 2 modulo 3. In this case, well, we have only 2 self-loops, which are unsurprisingly the problematic points, 1728 and infinity, which you can see already in this picture. And for the others, we have alternating in degrees. It's either in degree 1 or in degree 3. And what I also did in this picture was to emphasize from where the points come. So in this case, the twists, you only have 2 twists of the model curve. And the points coming from the rational points of the model curve are those which are white, while the others are those which are gray. So notably, you also have an alternating structure from where the points come. Okay, the other property is that actually every connected component has the same depth. So as you can see here, you have 1, 2, 3, 4 depth. And actually, this is constant throughout the whole graph. So also here, if you start from a point on the loop, you have the same depth. And this directly comes from the results we have seen before about endomorphisms of finite kernel over groups. Yes, and this depth is actually also dictated by the largest power of 3 contained in Q plus 1. So you can, just by looking at Q plus 1, you can immediately tell which is the depth of the Hessian graph. And finally, the order of each cycle is a divisor of the order of the maximal cycles. And the order of the maximal cycles in the Hessian graph depends on the multiplicative order of -3 modulo big N, where big N is the largest coprime to 3 factor of Q plus 1. So in this example, yeah, let's see, I think I wrote it down somewhere because I will never be able to improvise this. So yes, you have that 11 plus 1 is 3 times 4. So you need to look at 3 mod yes, you need to look at -3 mod 4, which is already 1. So this falls in the second case. And so you have to multiply the order of -3 mod 4, which is 1 by 2, and you get 2, which is the length of the maximal loop of the maximal cycle. And if you want an example of the first case here, you just need to look at the previous example. So it's -3 mod 10, I think, which has indeed order 4. So 4 is indeed the length of the maximal loop. Okay. So this is just to tell that we are able to say almost everything about the Hessian graph for Q equals 2 mod 3, and it's extremely regular, meaning that the depth is constant throughout the graph. The situation is slightly less nice for Q equals 1 mod 3, but if you add colors, it's nice again. So the graph is obtained as the union of 6 subgraphs. Okay, there are some intersections, as you can see that from the picture. In the Sage script I used for this, I prioritized the white points over the others. So it's always white when it can be white, because they are the points that come from the irrational points of the model curve and not from the twists. So they are more natural somehow to me. And then, yeah, actually there is a stricter coding. So the cubic twists are those with lighter colors, and their quadratic twists are the same color in a darker version. But yeah, this is just because I had too much free time recently. Okay, so we fully know the structure of the graph also in this case, because for each of these colors, we again have constant depth. Also, yes, we know that whenever you have some ramification occurring, you again have the big T attached there, except from some special cases that I will not go through, but they are essentially related to the points where you have some intersection between the 6 families. But what's probably more relevant is that overall you have just a constant depth over the same colors, and you even know what it is. So for 2 families, the depth will be 0, as you can see from the picture, I hope. For 3 of them, the depth is 0. Yeah, I was already worried that it didn't match up. 2 of them, FM equals 1. So the green and the white in this case. And the last one has depth that must be larger than 1, but can be arbitrarily large. Okay, so this again gives us, I'd say, a quite precise picture of what is happening over the Hessian graph. Okay, as I promised, I will now do something that is at least vaguely related to what we do, so to isogeny-based crypto, and do some rambling about supersingular elliptic curves. So most of us know that it's an open problem to find supersingular elliptic curves that are good for cryptography. So more precisely, there are protocols where you might need to start from a supersingular elliptic curve with a known endomorphism ring. But it's up to now, it's impossible to do that without a trusted setup or some multi-party workaround. So what we could hope is to try to leverage our knowledge of the Hessian graphs to do something related to finding supersingular elliptic curves, so identifying the connected components that contain them, and try to sample from them. Yes, also another more wishful thinking will be that you maybe start from an elliptic curve, you compute an iterated Hessian, which we said is quite easy because you can exploit the endomorphism on the model curve, and maybe you can give a criterion so that if you compute enough Hessians, you'll end again on a supersingular elliptic curve. But these are just like super hand-wavy ideas that might never turn out to work. What does work is that using the tools we introduced, you can at least rule out some connected components and from being candidates to contain supersingular j-invariants. So let's talk about supersingular components, so components that do contain a supersingular j-invariant. What we have is for now just necessary condition for a component to be supersingular. So the first thing we can do naively, and which we already did in past talks about this subject, is to look at the traces. And if you look at the traces, you again get some information. So you get the information that the supersingular components must contain elements with trace that is 0 mod 3. And yeah, this connection to to 0 mod 3 is not completely surprising if you think again at how the Hessian worked. So the Hessian kind of preserves the 3 torsion points. So it's not totally surprising that if you have a k-rational 3 torsion point, this is preserved. And yeah, this criterion works over FP. I should have mentioned that before. Over FP squared, I think you have some sort of equivalent criterion that doesn't, yeah, it's some kind of symmetric to this. But probably what is most interesting, and actually based on what we did in the remainder of this, on the previous part of the talk, is the criterion over p squared, which is probably the right place to look at if you look for supersingular j-invariants. And what it is interesting is that if you color the graph, the j-invariants all lie in the white part. So they all come from key rational points, from fp squared rational points of the model curve. And you do not need to look at the twists. This is actually very simple to prove because one knows that supersingular j-invariants are cubes in fp squared, and supersingular minus 1728 is a square. And finally, this perfectly matches the equation of the model curve we are using, so that this proves immediately that they must come from there. Okay, so here I gave you some non-examples because this is a legit prime and not a prime squared. So they are not expected to fall in only white or only gray vertices, and it is the case. Also, if you pick a prime that is 1 mod 3, but again, only a prime and not a prime squared, you see that you also have some gray vertices that, okay, of course, they're not gray because I colored them in red, but trust me that they would be gray. So there is nothing. But if you look at the squares, you see that the supersingular j-invariants do fall, as I said, in the white part. So this works for 2 examples, so it works, as we all know, always. But of course, this is not a super great achievement because, as I said, the proof uses something that was already known, and you are just cutting, I think, in 6 parts the space over which you need to look at. So this is at least a hint that the model cure we are using is a nice cure to look at supersingularity. It's less clear how much this relates to the Hessian thing and just it relates to the model curve. But anyway, what's probably the most important thing is that we draw some nice pictures with many colors. So yeah, with this happy note, I conclude my talk, and thank you for your attention.
Thank you. Thanks for the talk. Does anyone have any questions?
Maybe I can ask a question. So this Hessian map is, as you've been saying many times, very related to the 3 torsion. Are there other, like, does there exist similar things for like other n torsions? Or a very vague
We are
question,
asking ourselves the same question, actually. Well, but yeah, it's hard to find an answer. I would say that the Hessian has something special because the inflection points have something special. So this trick that you get another object which intersects you at n squared points, say, cannot work forever because at some point if you go over if you have 10 common points, you probably have the same elliptic curve. I guess there is some Bezout-like result that forces you to have a small intersection between two cubics. So this is not expected to still hold. One might ask, is there maybe some Lattès map that has a geometrical meaning over the set of j-invariants? Because this is the actual weird thing that is going on. So I think at least to my knowledge, this is the only situation where you have an operation on an elliptic curve on top, which is this endomorphism psi that I was introducing, which is on the side of j-invariants, which corresponds to an operation on the j-invariants that has a meaning, because Otherwise, yeah, for any modular curve, you could just pick an endomorphism on the model curve and see what happens on the j-invariants. But I don't think this gives rise to anything geometric. So yeah, for sure it will be interesting. I'm not super confident that it still works because the Hessian seems to be very specific to these inflection points that are, yeah. So the number 3 is special in itself, and probably you cannot extend it to, at least for elliptic curves. Maybe higher dimensional stuff you can do something else. This might be interesting, but we did not investigate.
I see. Oh, cool. Thanks.
Thank you.
Yeah, I was gonna ask on this higher dimensional thing if that is like an analog of this Hessian that you know of. Like if it just holds more generally, or
analog, yeah, I think the only, if you look at second derivatives, no, I think, because there are only 2 situations where taking the determinant of that matrix leads you to a variety of the same form. And the other case, I think, is slightly disappointing. It's like 4 points, so over a 3-dimensional space or something like this. I don't remember. It was in Daniele's talk. So yeah, you might ask if there are higher order derivatives that lead you to something. For this, I don't know. And I also don't know if there is geometrical meaning to this. But yeah, it will be cool to investigate. Yeah, but for the Hessian, for sure, it doesn't work over higher dimensional varieties because the dimension is not preserved.
yeah, I was thinking maybe you could go like the modular curve route and think what the analog of that is, and if there is some operation that will get you somewhere. But it may be that it's just too complicated in higher dimension. I don't know.
So you will have the modular curve on one side, and you will still with the same, but what would you project to? Not j-invariants, you need something.
Yeah, you'd need like Igusa invariants or something. I don't know. Okay, I think it would be a lot more complicated, but yeah, I was just wondering if there was an analog out there. Maybe it's a bit.
Would be cool. Yeah.
Is there a theory of so Lattès maps had like elliptic curves as like integral part of the definition, but if you just replace the elliptic curve by some higher genus curve, is it I guess it has a different name, or is it even studied?
I think it has been studied because we were naive and we discovered this after finding out most of the results in the paper. But yeah, people expert into dynamical systems know quite a lot about them. So I think the generalization that has been done is for algebraic groups in general. So you replace elliptic curve by algebraic group, and you get something. So yeah, you want the algebraic part, which means that you need, at some point you cannot just project on a field. You will project to something 2-dimensional, I guess.
Yeah, no, I guess that's...
Yeah, but this has been done. I think also Mark Huben has done something on this topic, and he was the one who suggested us to implement this Lattès thing in our article, which turned out to be a great suggestion indeed. So yeah, he did some work on this.
Very cool.
Yeah, sorry, maybe I can make use of the opportunity.
Feel free to take over.
Now that my name was mentioned, to ask you a question.
Exactly.
So could you go back to the slide where you define the projection maps? So like the pies.
Like here?
Maybe.
Or before?
Maybe before this.
You're in the first test here?
Yeah, that one.
Yeah.
So I couldn't help but notice that so both of these maps are quotient by automorphisms of EK.
Yes.
So the first one is like the quotient by the automorphism multiplication by -1, right? So you basically get like a
Yes.
Kummer line. And in the second one, you have, well, the curve SCM by third root of unity. And then I guess if you compose this map with multiplication by -1, then you get a degree 6 automorphism.
That's correct.
For which pi is exactly the quotient by this. Is that also how you got to this these inverse maps? Basically, like this the field that like how you got these quadratic and sextic twists.
Yeah, I guess this might be the intuition behind that. It's not how we got there, because we got there more brute forcefully by looking at the pictures and trying to build groups inside this pre-image of P. But yeah, I think it must be related. So because this is really part of the definition of lattice map. So you're actually taking a quotient of the elliptic cure by groups of automorphisms. And yeah, if you look at them, you already know what P will look like. It's a general result, and yeah, it's not too surprising. Yeah, I think you can always reduce to having P of this shape.
Yeah, so I guess the pre-image of the projective line is basically all of the x's as well as all of the x's multiplied by this. Well, I guess all of the points under the automorphisms, right?
Yes, exactly.
So I guess you got like all of the images of the points on EK over the base field under either the quadratic or the degree 6 automorphism. So
say it again. So you go back. You said you go back to the points here.
Yeah. So I think if you look at the base field, so you take P1 of K, and you want to understand the inverse image of that, then, well, a priori, the first guess is like EK over K, right?
Yes.
But that's not completely correct, because there's more options.
Indeed.
And because the pi is exactly the quotient by this automorphism, the pre-image should actually be the images of EK over K under the whole group generated by this automorphism, right? So that in the first case it would be EK union its quadratic twist, and then in the second case would be EK union all of the sextic twists. Yeah,
that's correct. Yeah, I think it's okay. You're right. This might be an easier way to, because I expressed that in terms of sending back the twists to the calculation points on the twist to the original cure. But I think you're right that it's maybe more natural to prove it if you look at the action of the automorphism group. Is this what you were saying, right?
Yeah, and then kind of my follow-up was about these colors. So you had these graphs where all of the components had like a certain color, and this kind of course, I maybe didn't fully remember your definition of the different colors, but this had something to do with the twists, right?
Wait, I missed the last part of your sentence. I think there was the colors. So yeah, I go to the colors, for example, here, or maybe even more elaborate here.
Yeah. So does this just have something to with the
it's only me.
that
Maybe
over
Zoom
this
is censoring
particular
your
thing
words.
overweighs you.
Yeah. Well, I sorry. Yeah, every time you try to ask this question, there is. I don't know if it's only me, but
No, I think your connection is a bit poor, Mark. Mark? Ah, yeah.
Okay.
okay.
I think Ricardo has a question in the chat. How long does it take on average if you start computing Hessians of curves from a random one to encounter a supersingular one?
Yeah, I would say too much for now. I think it's not so far. It's not getting much better than. Also, there is a little issue. So the graphs could be ramified. So it doesn't always work because you could have some supersingular component hidden in a branch. So you would also need to go backwards. But if you stick to the cycles, yes, we don't have precise estimates so far. We have a master student that might be working on this. So far, the impression is that they are not close enough. So since they are probably randomly scattered, if you pick a large prime, that probably doesn't really work. But yeah, it's surely something we want to investigate. Also, when you are on the cycle, you can also use discrete logarithm computation. So especially when the model curve is supersingular, I think this is quite efficient. And so you might check if two supersingular vertices are on the same connected component and how far they are quite easily, I think. But yeah, we haven't experimented so much on this, but for sure it's a very natural question. Yeah. Thank you.
All right, thank you. Are there any final questions?
Doesn't seem like it. So yeah, thank you again very much, Marzio.
Thank you guys for having me here.
Great talk. Just wanted to quickly mention that in 2 weeks we will have none other than Ricardo himself giving a talk on a mystery topic for now. So yeah, until that time, bye-bye. Well, we can end the recording.
Yeah, let me end it.